Problem 14. This problem was written back in 2002 when the Olympics, the Winter Olympics, were nearby. My wife and youngest son went down. My oldest son was actually working as one of those helpful people from BYU that was helping to run the events. Anyway, the only event they could get into was the bobsled, and they came back. My son was so excited I wrote this exam question. In this case, we have bobsleds being launched by a spring. They go down a frictionless ramp and they try to get as much air as possible, see how far they can go down the landing field. Now the first question was only worth 2 points. And it's the same question that you had at the beginning of every single homework problem. What's the varic?
0.
0. It's got to be 0. And that gets you one of the 2 points. The other point is giving the justification. And remember, varic, it's only external varic we care about. And if we draw a free-body diagram for that bobsled, the Earth is part of our system, so that we can talk about the gravitational potential energy. So this is an internal force. This is the only force we have to worry about. The only external force. And it is always perpendicular to the motion. Now you see that I just violated one of the most fundamental rules of free body diagrams. I put something that's not a force on the diagram. I will burn in heck. I'm sorry. But it doesn't matter where we look in this motion, the normal force is always perpendicular to the way the cart is moving, the bobsled is moving. And so I get 0 there. Now this is where it gets interesting rather. We're told that when the bobsled gets here at B, it's going 50 meters per second, over 100 miles an hour. And the question is, what's the spring constant of that spring if we cocked it 4 meters to get started? Now this is an energy problem, so I have to decide what kinds of energy I have. Well, I always ask myself the same 3 questions. Is anything with mass moving? No, not yet. Is anything up off the floor? Yes. If I choose the lowest point in the problem to be my floor, then it's 120 meters up off the floor. The last question is, are any springs stretched or compressed? Oh yeah. Then I go to my final event and I ask the same questions. Is anything with mass moving? Yeah, 50 meters per second. Is anything up off the floor? Yeah, 20 meters up off the floor. Are any springs stretched or compressed? Not anymore. So the buckets that are filled are gravitational and spring to begin with. Since there's no external varic, the energy is conserved. And now that energy is kinetic and potential gravitational. Now, this very quickly turns into math. I write which buckets I have at the initial and the final locations, and then I put in the formulas for those buckets. Now you'll notice that everything's in black except for K. And that's because I know everything except for K. They're all knowns. Quick question, can I just cancel the mass? I got mass on the left, I got mass on the right. Can I cancel the mass? No or heck no?
Heck no.
Heck no. It's not in every term. I got it there, I got it there, I got it there, but not there. Okay, so I cannot cancel the mass. I plug in all the things I know, and there's just one unknown. Now, if that just looks scary to you, if that looks like you could never figure that out, this next exam is going to be a nightmare. If that's just algebra to you, and algebra is easy, you're going to be fine. The answer is 25,000 newtons for each meter. Check to see if your neighbor got that, please. Okay. We're asked to find the acceleration of the bobsled at point B. Now, at B, the bobsled is not speeding up. It has been speeding up, but not now, not at B. At B, the bobsled is not slowing down. It will be slowing down in just a moment. But at B, it's in transition. It was speeding up, and it's about to slow down. That's the point where we take our foot off the gas and move it to the brake. At that point, the only kind of acceleration we have is turning. And it's in a circular path, and so that's going to be centripetal acceleration, v squared over r. The v is given as 50 meters per second. The radius is given as 100 meters. That gives me an acceleration of 25 meters per second per second. Now, when this was on an exam, people said, well, it would be 25 meters per second, but really not, because it's not speeding up or slowing down. No, this really is. I mean, this is a big acceleration, and you feel it. When you hit the gas, you're thrown backwards in your car. When you hit the brake, you're thrown forwards in your car. When you feel, when you turn the steering wheel real quick, you're thrown the other way. Now, in this case, these Jamaican bobsled team, they feel it because they are headed down and suddenly the bobsled starts going up. They keep going down and it feels like they're being crushed into their sled. They feel like they each ate 27 Big Macs. Okay? Their apparent weight becomes huge. Okay? Now, we want to find that apparent weight for the whole bobsled. If we draw a three-body diagram for that bobsled, it had better scream up. And that's because there's an acceleration up. How loud should the scream be? Well, that's given by F net equals ma, where the mass is 80 kilograms, the acceleration is 25 meters per second up. That means this diagram has to scream up by 20,000 newtons. That's quite a scream. Now the weight force is just mg, that's just 8,000 newtons. So how big does that normal force have to be on the bobsled? Tell your neighbor real quick. My scream up has to be 20,000. Okay, I hope everyone said 28,000 newtons. Good. Okay. Now, you've noticed that every single homework problem that you were assigned for today, and both of the problems on the tutorial homework that was due yesterday, had circular motion involved. And that's because these energy problems give us a really good opportunity to, pardon the pun, circle back on rotation, circular motion. Okay, so you can pretty much bet on the fact that you're going to have a problem like that on your exam, one that involves circular motion. Now the last part of this problem asks, how fast will the Jamaican team be traveling right before they land on the landing field? And again, this is an energy problem. If I look at the energy at B, they're moving, so there's kinetic energy. They're up off the floor, so there's gravitational energy. The spring is neither stretched nor compressed, so there's no spring energy. That total energy is going to be conserved if we ignore air resistance. Remember, it's a frictionless ramp. And now, if we choose the height of that landing field as 0, all of the energy is in the kinetic bucket. There's no gravitational energy. I write a formula for each of those buckets. What about now? Can I cancel the mass? Yes, every term has mass, so I can cancel it. I solve for the one unknown, and sure enough, it's going to hurt. 54 meters per second. Going pretty fast. Now, I assume that everyone watched Disney's classic movie, Cool Runnings, so that you know why I'm using the Jamaican team. Okay? Jamaica's got a bobsled team. Okay. Any questions on that problem? That is the energy problem. We dress it up different ways, but it's always that. And it's almost embarrassing because you saw that in 2 steps it stops being physics and suddenly becomes algebra. When we take this next exam, it's partially going to be an algebra exam. I'm ashamed of that, but I can't find a way around it. Okay? I imagine myself as a math teacher, and it just gives me nightmares. Okay. Turn to your neighbor and answer this question. What is momentum? What is momentum? On the field. Oh, if you go all the way. That should give us the same. And I got 54. I don't know. She did something. Okay. If I were to say that senator has a lot of momentum, or that idea has a lot of momentum, or that freight train has a lot of momentum, what does the word momentum tell me about the senator, the idea, or the freight train? Raise your hand, brave soul. Where are you? There you are.
It's hard to stop.
It's hard to stop. Okay, it's hard to stop. That's a bad day on a train. It's just how hard it is to stop something. Okay? Now I have a question for you. Jake. Skateboard? Jake just confided in me that he's an avid skateboarder. Here is actually a picture of Jake going down Main Street. Jake, how fast do you go? He claims 50 miles an hour, but that seems a little high, but that's what he says. Anyway, Jake is going down Main Street 50 miles an hour. Right next to him is a Mack truck, also going 50 miles an hour. Which has more momentum? Which would be harder to stop? Jake or the Mack truck?
Mack truck.
Yeah, the Mack truck. So clearly mass is important. Now, is that Mack truck always going to have more momentum than Jake? No. Park it at Albertsons. It's not hard to stop a parked truck. And so it's more than just the mass. Okay? The mass matters, but also the speed. And it turns out that momentum, how hard it is to stop something, is just the product. And we label it with a P. Now, that troubles me. We use P for power and pressure and all sorts of things. And here we use it for momentum because momentum it's silent like pneumonia. I don't know. I have no idea. It's just historical. Okay. Now, can you, with your neighbor, find an example of something that would be hard to stop, have a lot of momentum, but doesn't have very much mass? Anyone?
Bullet.
A bullet. 23 years teaching in Montana, that's the only example I've ever got. A bullet. It has a lot of momentum because it's going very quick. Let me give you another example. I went to high school in the island of Guam. In Guam, nobody had windows. What we had were metal louvers that could be closed, but not so closed that the geckos couldn't get in. And the reason we had louvers instead of windows is because we had coconuts. They were just littering our lawn everywhere. And we also had tropical storms. And whenever a tropical storm came around, those coconuts looked like cannonballs. Yeah, that's the way they acted. Now, right next to where our house was, in the jungle, there was a whole village that had been wiped out. There were roads, there were foundations, there just weren't any houses. And that's because before we moved to the island, there had been this huge, huge storm that had just wiped that village out. Now, I had friends who had grown up on the island. They had pictures from that storm. And one picture that I remember vividly was a telephone pole that had all sorts of little junk embedded into it. Pieces of glass, pieces of metal. And they were just going so fast, they didn't want to stop. What about an example, or a couple of examples, of something that would have a lot of momentum, hard to stop, but not going very fast?
A planet.
What's that?
A planet.
A planet. Okay.
Train.
Train. I'm just thankful you didn't say Greg. Okay. Anything with a lot of mass. Okay. This space shuttle, even when it's just lumbering down the runway, is very hard to stop because it has a large mass. Now, of course, lumbering down the runway is not the way this is supposed to be used. Its cruising speed is about 17,000 miles per hour. So at that point, it's just way hard to stop. Way hard to stop. Now, I need a captain. Have you owned a boat? Have you been a captain of a boat?
No.
No. Would you like to be?
Sure.
Good. Okay, what's your name?
Roz.
Roz? Okay, Captain Roz. Okay? Captain Roz is the captain of this super tanker. Roz, Captain, your job, if you will accept it, is to park it at the dock. Okay? To park it, you've got to take its momentum, which is big, and you've got to change that down to 0. Now, one way that you can do that is if you just turn off the engine and let the water in front of the boat push against the boat, it will bring the boat to a halt. Now, Captain, how long, according to your Mickey, before you want to park, do you think you should turn off that engine?
Quite a bit of time.
Quite a bit of time, an hour and a half. Now, have you known Captain Roz for quite some time?
I have done
Would you, in all honesty, say that she's a patient captain?
that. I would not say she's
No, she is not. She is not. And she does not have to be, because she can stop that boat in just 23 seconds. How? Just ram it into the dock. 23 seconds and 3 city blocks later, it is stopped. Okay? It actually happened down in New Orleans, right there at the marketplace. So here's what the thing is. If you want to change momentum, you can do it with a small force if you're willing to wait a long time. Or you can do it quickly if you can supply a very large force. Now, this combination of force times time is what changes momentum. It's called the impulse. Okay? Now, I want you to look at something here. When we were talking about energy, it was force times distance that changed the energy, the Vec. But when it comes to momentum, the initial momentum is equal to the final momentum, except when it's not. And that's when I've got an impulse acting. That's how you change momentum, is with an impulse. Now, that formula of force times time only works when the force is uniform in time. If it's 50 newtons, 50 newtons, 50 newtons, 50 newtons, 50 newtons. But in most problems, that's not the way it is. If you hit a ball with a bat, the force acting on the ball is going to start at 0, when the ball first comes in contact with the bat, it's going to ramp up to some maximum value and then ramp back down. Now you can calculate the impulse either by using calculus, which isn't our first choice, or you can just take the average force over that time and multiply by the time. Does that make sense? Now I have stalled long enough. It is time to do the bet of death. This is my family. We're a handsome crowd. I have invited Paul Ruckheimer, the assistant of death, to come down and swing the sledgehammer. You may notice that he is large. He is strong.
Thanks, Craig.
Well, I didn't mean large like me. I meant big and large. Okay. This is the hardest part at my age. Okay. At this point, I am required by law and by the university attorney to issue the following warning. Do not, I repeat, do not try this at home. I am a trained professional. I did not start with 1,000 nails. I started with 1 nail, worked my way up to 10 nails, and now yeah. Doing this with 1 nail, that would be biology, right? I mean, if you take 1 nail and you park my 150 pounds on it, that's gonna make a hole. Wait, what are you laughing about now? That's rude. Okay. Okay, so it's not 150 pounds. Now, if I take a nail, a sharp nail, and push with 1 or 2 pounds, I'm going to make a hole. There's going to be blood. But if I take my weight, and let's, just to make the math easy, let's say it's 200. That, I wish it were. 200 pounds spread over 1,000 nails, what would each nail be pushing? Just math.
5 pounds.
Yeah, 1/5 of a pound. 1/5 of a pound. So that's not going to make a hole. So having a lot of nails is really a good thing. But that's not what's going to save my life. If I were to just lie down on the floor here and ask Paul to hit me with a sledgehammer, he'd do it. But again, it would be biology. There's something else that's going to save my life, hopefully. So let's, without further ado, let's do this. Whoa, too long. Okay, chest plate of death. It used to be the chest plate of death, but these days it's more like the tummy plate of death. I don't know.
And then you said that was down?
That would be the way I'd choose to do it. That way it goes out and hits you.
I mean, now I'm left-handed, so I have to swing from over here.
Oh, get up here.
All right.
Wait, you have to get up on the table and swing.
I do.
Yeah,
I've done it.
that's okay.
I've never done it.
Oh, you've never done it before?
I swung it once, but I stood on the ground.
Oh, just stand up and take a big
All right.
swing. Scream.
Okay.
Do it your hardest. Okay.
If I miss, you'll have to teach your class.
Paul.
All right.
Paul, think about it. If you miss, you get my job. It is not good. Any questions? Any questions?
All right. There we go.
Anytime. All right, let's give him a hand. Uh-oh. Some explaining to do. Okay, let's talk about that. Which way do we want to stop that sledgehammer, quickly or slowly? With your clicker, tell me, which way do we want to stop that sledgehammer, quickly or slowly? Oh, thank you, Paul, I'll get that.
Absolutely.
Okay, last call. Oh, quickly. Maybe I didn't ask the question correctly. Let me ask it a different way. Which way do I want to stop the sledgehammer? And remember, I understand Newton's third law. And Newton's third law says that if I put a big force on that sledgehammer to stop it quickly, what? It puts a big force on me to kill me. I want to stop that sledgehammer as slowly as possible. Which piece of equipment just saved my life? The cinder block of life, it should be called. Without that cinder block, the sledgehammer would stop almost instantly. It took time to crash through that cinder block. That cinder block was acting like a funny looking airbag. Imagine if you hit something with your Toyota and cinder blocks just started jumping out of the dashboard. That'd be great, wouldn't it? Now, I have to tell you, this demo has not always gone well. 23 years ago, my first semester teaching, I was really worried about this demo. So I went to an older professor, Larry Kirkpatrick, and I said, Larry, how hard should they swing the sledgehammer? He said, oh, trust the physics. They can swing as hard as they want. You'll be fine. So I went down to my class. I asked a student to help me, a student that I knew from church. He was an older student, and I trusted him. His name was Ralph. And I said, Ralph, would you swing the sledgehammer? He said, sure, how hard? Hard as you want. I'll be fine. I forgot to notice that Ralph was a giant of a man. He took a great big roundhouse swing, and he came down with all of his mighty might, and he missed the center of the cinder block. He hit the edge. The professor just sorted it. Hit him with a rock. Hit him with a rock. So, there was one other time that it didn't go well. I was going to do a demo show for a charity, and my son wanted to lie on the bed of death. My wife said, no way, no how, not my firstborn baby. And we got in the car to go to the event. My wife was not going. We looked at each other and said, let's do it. And so I swung as hard as I could. I hit it just perfect. And my son, so excited to be alive, pushed himself up, did a high five with me, and I said, blood. Oh. He was so excited he'd pushed off the nails and put holes in his hands. And when we got home, we were in trouble. Okay. Now, we want to stop that sledgehammer as slowly as possible. Now, in chapter 8, there's one grand equation, just like there's one grand equation in chapter 7 that governs work and energy. That equation is the impulse-momentum equation. Impulse changes momentum. Now, if I subtract the initial energy from this equation, I get Verk is what changes energy. And Verk being force times the distance. And you compare that to this equation up here, the difference is that we're talking about the time that the force acts and not the distance through which it acts. Now there's two ways that we typically use this equation in everyday experience. The first way is we have a change in momentum that is fixed. There is nothing we can do about it. You're going 30 miles an hour in your car, you hit a brick wall, the change in momentum is what it is. And we want to minimize the force by stretching out the time. Turn to your neighbor and come up with at least 2 examples of that from everyday experience where you would lengthen the time to minimize the force. Go ahead. Talk to your neighbor. I will share with you that this shirt is kind of dorky. but it also hasn't always been a good idea. I had an occasion one evening to have this whole room filled with Cub Scouts from Bozeman and their families. And it turns out that their families meant they had little brothers and sisters. And so when I turned around with this shirt, they're just, and the mothers were not impressed. It was not good. Okay, what examples did you come up with where you increased the time? Raise your hand, brave soul.
Using your bike brakes slowly so you don't flip over your handlebar.
Okay, yeah, there's a couple of ways that you can do your bike brakes. You can just lock them down and go up and over, or you can just gradually do it.
Parachutes when you're skydiving?
Yeah, parachute, okay. You open that parachute, and the longer it applies that force, the bigger your change in momentum. You'd like the change in momentum to be big enough so that you hit the ground at a reasonable rate. Do any of you parachuted? Raise your hand. Yeah, don't do that again. Okay. What else? There was someone over here.
Shock absorbers?
Shock absorbers. That's a perfect example. That's why you have shock absorbers, is so that you don't feel every big jolt in the road. Give you another example. If you're jumping from a height, did your parents teach you to lock your knees? Is that what they taught you? I hope not, because that's just going to shatter your knees. What you want to do is you want to land with your knees flexible to increase the amount of time over which you come to a halt. Likewise, if you're catching a fastball, you don't catch it like that. You catch it like that to increase the time. Give you one more example. Many years ago when we were living in Seattle, a friend called my wife and said, "Hey, we're re-roofing our house next Saturday. Could we borrow your husband?" My wife said, "Sure, I'm not using him," and volunteered me. Now, she forgot momentarily that her husband is afraid of heights. And when I got there, I found it was a 2-story house. So I got up there and I was very nervous. I was crawling around on my hands and feet, scared to death. The manly men who came were just walking around the roof like it was nothing. But one of those manly men had brought his son. His name was Christian. He was about 11, 12 years old. And he felt the same way about that roof as I did. And he was crawling around on his hands and knees and mistakenly crawled onto a piece of sheet metal which turned into a toboggan, and he went down off the roof. Now, as fate would have it, fortunately, he landed on a wooden deck and crashed through the deck. He broke bones. He was in the hospital for quite a while. But he's just fine now. He's he's in his 20s and healthy. Now, if he had landed instead on a concrete pad, that would have been a different ending to that story. It was the time that it took to crash through that wooden deck that saved his life. Now, there's another way to use this equation. There are times when the force that you can deliver is fixed by some parameter that you have no control over. And you want to apply that force for as long as possible to get the biggest change in momentum you can possibly get. An example of this might be the length of a rifle barrel, where you push on the bullet as long as you can to get it going as fast as you can. Okay? With your neighbor, turn to your neighbor and find a couple of other examples of this sort of use.
What do you got?
Okay, what did you come up with? Brave soul.
She had a good one.
Cowards, all of you? Oh,
An airplane on takeoff.
an airplane on takeoff. Okay, you want that runway to be longer than 100 feet. You want to just keep on applying that force to get going as fast as you can. Excellent.
Pushing a kid on a swing.
Okay, pushing a kid on the swing. Have you ever done the underdog? No?
Yes.
Wait till you have grandkids. They love the underdog. You just keep on pushing as you go all the way under. Yes, good example, Elizabeth. What other examples? What about the big surgical tubing that you put on those wrist rockets? The slingshots? I mean, it's really, really long, so you pull it back like this so that it's pushing on that rock or whatever you're shooting for a long time. Here's another example. This is just what I've heard. I've heard that if you're in a bar at 2 in the morning and you get in a fight and you can only apply so much force, that you want to keep in contact with the other guy's jaw as long as possible to impart as much change in momentum. Now, I've never been to a bar and I've never been in a fist fight. Just hearsay. Okay? Hearsay. Now, there's one last big idea that we've skated past, and I'm going to introduce this with a hypothetical. Suppose that Greg and his friend Jeff Adams are both walking down the street and a student recognizes them. And that student drops a couple of flower pots from the second-story window, and those flower pots hit Greg and Jeff going 20 meters per second. Now, in the case of Jeff, that flower pot bounces off his head at 20 meters per second. In the case of Greg, it stops. Now, the question is, if the delta t for that collision is the same for both Greg and Jeff, who has the worst headache? Who had the biggest force applied to their head? Talk to your neighbor. Which is it? Greg or Jeff are the same? Okay, let's vote with our hands. Those who say Greg has the bigger headache. Those who say Jeff has the bigger headache. Those who aren't sure. Okay. The reason we divided the class like that, suggesting there's confusion, is because I lied to you. I told you over and over again that momentum was mass times speed. That's a lie. Momentum is a vector. And it's mass times velocity. And the direction is critical. It's critical. If I have a baseball coming in at 50 miles an hour, it's hit by a bat and it goes off at 50 miles an hour, that seems like the same momentum. Mass times 50 miles an hour. But in one case it's going east and in the other case it's going west. Those are very, very different momenta. And if I want to know how different they are, I do what I always do. I take those two vectors and I put them tail to tail. And I ask myself, what would I have to add to this vector to turn it into that vector? Well, I would have to add this. There's the plus sign right there. This change in momentum takes the initial momentum, brings it down to 0, and out the other way. Now that change in momentum is caused by the impulse, which is the force times the time. Now if we go back to my example, in the case of Jeff, that flower pot bounces. And that means the change in momentum is twice the magnitude of the initial momentum. If I look at the case of Greg, it stops. And that means the change in momentum is the same magnitude as the initial momentum. Jeff's head not only has to stop the flower pot, it has to stop it and throw it back up in the air. That is a much greater force required if the time is the same. And if Jeff is putting a much greater force on the pot is putting much greater force on the Jeff. Now, I have to tell you, many years ago, Jeff and I were going to our cars out there in the parking lot, crossing Grant Street, on a very, very icy February afternoon. And as we were crossing the street, this great big huge older car just came, it slammed on its brake, couldn't stop, it just came racing through the intersection. Jeff and I both turned around, put our hands on the hood, and it pushed us right through that intersection and down Grant Street. I'm terrified. I look over and Jeff is just smiling, and he says to me, "Is this one of your students or one of mine?" Folks, that's all I had prepared today. We went a little faster than normal. So why don't you just take the rest of the time off and get yourself a donut.